Good afternoon, everyone. Thanks so much for joining us and welcome to the Bulkley Valley Research Center December seminar series presentation. My name is Dawn Hansen. I'm the Executive Director of the Bulkley Valley Research Center. I'd like to acknowledge that I am hosting today from the Gitumden Clan territory of the Wet'suwet'en Nation on the banks of the Wet'suwet'en River. I'd like to thank our funders that help make the seminar series possible, the Bulkley Valley Credit Union, the Bulkley Valley Community Fund, and Wet'suwet'en Community Forest. And I'd also like to thank those of you that are members. Membership is really important to the center. It shows your support in us, and it allows us to have kind of a bit of a captive audience that we can share our seminar series with, but also for you to spread the word about what we're up to, and for us to also be an avenue for you to share your research or your work that you've been engaged in over the years, and use this as a networking and learning platform. We're really thrilled to have Brad and Ashlyn this afternoon presenting today. They're going to talk about the Alkali Lake Wildfire from 2018 that burned well over 100,000 acres and was still smoldering a year later. As the Alkali Lake fire begins the process of regrowth, they're documenting the types of forest fuels that are growing to better understand how the fire threat will return to the area over time. Brad began his protection in BC Wildfire Service career in 1984 in Dease Lake and came to Smithers in 1995. He's held a wide variety of positions over the years: initial attack crew leader, helicopter spotter, air attack officer, and he's now senior wildfire officer of operations, and has served as operations and as the senior wildfire officer in prevention. He was also sole proprietor of a forestry company from 95 to 2005 and has worked extensively in the forest industry in both government and private sector positions. Ashlyn's joining us from, well, typically from Victoria, but is in Kamloops today. He was completing his Bachelor of Science and Masters of Science in Math and Statistics at the University of Alberta, and he worked as a physical scientist with the Pacific Forestry Center in forest remote sensing research. He's worked as a consultant in science, engineering, finance, and health service industries, and is currently working with BC Wildfire Service as the senior data scientist in the Predictive Services Unit to develop AI sensing applications for increasingly proactive situational awareness. And it sounds like together they make a dynamic 1-2 team. Thanks very much to both of you for your time today, and looking really forward to this.
Super. Thanks, Don.
Thanks so much.
And thanks to everybody that signed in. Hopefully with this presentation, there's a little bit of everything for everyone in here. So we'll just jump right into it. I too am presenting from Smithers, again on the unceded Gitumden Clan territory, home of the Wet'suwet'en Nation, where I work and play, the emphasis on play. Beautiful country. So this presentation today is going to kind of be two parts. I'm going to set the stage, and then Ash is going to get into sort of more of the science side of things. But just first to frame things a little bit, this is a picture of the Alkali Lake fire. And just from an informational perspective, it was actually, I don't have the exact number, about 15 to 20 lightning strikes that started in 2018, started different fires, and they all combined to burn approximately 120,000 hectares. And of course, it caused a lot of destruction, but like with all fire, it also did some good on the landscape. And just as a point of interest, I assume you can see my cursor. This area in here, the reason that didn't burn was there was a fire earlier in the year in April that I attended to down there that burned. And so when this fire got going, that burn scar helped prevent the fire from burning in there. So just a bit of interest on that. And for reference, Telegraph Creek, Alkali Lake is actually just back here. The Stikine River, the Tahltan River, Toohey River, Tanzilla River. So we're going to talk today, I'm going to provide a little bit of background, kind of what spurred this along. We're going to look at the methodology. The field portion is mine, and the office portion is Ash's. And then we're going to look at the results, which Ash will present, and then future work. Because of the 2021 fire season, we got started doing some work, but of course, everyone can appreciate last year was busy. So we weren't able to finish and get as much plot work later in the season as we would like to have. But that's just the way it goes with fire. So that's where we're going to go. And just of interest, this is a picture from 2019 where we had a lot of holdover fires from 2018. And just for perspective, the crews are digging down because the fire down where his boots are was actually burning underground underneath all that organic matter. And to the right, you can kind of see where it was charcoaled a bit. And there is an interesting layer down there. I'd be really curious what that is, but it almost seemed like a coal charcoal layer. And I'm not sure if that has something to do with mounted Ziza way back when, but very interesting, very challenging. They cut these blocks out with chainsaws. So how did it all start? 2019 fire season, as I mentioned, there was a lot of holdover fires from 2018, 20 or 30 of them throughout the area. Some were inside the fire, but others were right on the edge of the perimeter, like this one that I showed the picture of. And so it gave us a real good opportunity to evaluate the 2018 burn. We were down there already. And of course, we were curious, how intense and how severe was this fire? We were able to do a lot of flying around and recognize that most of that burn was very intense. For the most part, there was not a lot of forest fuels remaining. However, we noticed that there was already this fall down effect starting, and you can see it in this picture, primarily in the spruce that burned, and in some of the deciduous where there was those deeper organics, and it basically undermined and allowed these fuels to burn over. Also add that there's a lot of strong winds in Telegraph Creek. So what is the reburn potential now? And if there is not a big issue right now, how long until it is an issue? And can we start to look at managing this before that 120,000 hectares comes back to cause us some grief? So what are the management implications over time? And ultimately, the question from a sort of selfish response perspective is, what is the actual hazard out there? While we were doing this, unbeknownst to us, Ash and his group of Joanna, Alex, and the Predictive Services Unit were already looking into using imagery to try to discern different forest fuels based on color bands to create a minimum viable product. So what's the least amount of effort we have to do to kind of get the maximum results out of this? And just this slide is just a quick one to take a little bit of a right turn. You're going to see some conventions like C5, D1, S201. All these is our standard fuel types that are recognized across Canada that we use to determine fire behavior. There's 16 of these. Basically, there's an algorithm. It takes all the VRI labels and it puts them through an algorithm and it forces them into one of these broad fuel types. So sometimes there's a good match and sometimes there's a poor match. But when you see these letters here, it'll make sense, especially on the next slide. So what do we have in place post-fire to help determine what kind of fuels are growing back? This is sort of a bit of a key, and it's also factored in when we run the algorithms through the VRI. So from a recent burn, I've highlighted the three that are the most common sort of down in the Telegraph Creek area. So if it was a conifer forest, dense crown closure, or it was a mixed wood or non-forest, you can see TSF is time since fire. So N is non-fuel. At 4 to 6 years, it should be a deciduous type, and at 7 to 10 is a C5 type. None of these cause us a lot of concern from a hazard perspective. Same as down here. M is just a mixed wood, so a certain component of deciduous and a certain component of deciduous, or of conifer, sorry. But those fuel types, same as this deciduous again. This is the only one where in places where it was grass or shrub, comes back to a grass in 4 to 6 years and can cause us some concern. So from this basic chart, there really shouldn't be any issues out for at least about 10 years based on this. But what we've found in the past, this is a fire up near the Yukon border in 2010, burned 35,000 hectares, primarily in spruce, some pockets of pine and mixed wood. We had a lightning strike and a reported start in 2016, And the strike was actually within the old burn. And when we heard that, we of course didn't think that there was going to be an issue because only 6 years have passed and that fire too burned pretty intense. But as you can see, this fire actually burned 4,800 hectares, caught us by surprise, somewhat I'll say, and looked to threaten the highway again. This is Highway 37. So once we got out there, we realized what's happening is all this fall down stuff, grass was coming up underneath it. So you had your fine fuels. You also had all this timber that came down. So it was almost like a slash. So whenever the wind picked up, it would just whistle along. And that's what created this. So we realized that some of these fires can reburn sooner than what we were sort of looking at from a general perspective. So fast forward to 2020, where we decided to start to look at this a little more in depth. The fire weather indices were climbing in Telegraph Creek, where our weather station is. And the concern was what's left in that burn? Like, should we be concerned within that 120,000 hectares of anything, of a hazard? We didn't believe so. But what we did is there was an app that was created, not specific to this, but there was an app that was created. And for me, that's always interesting because I'm not used to taking an app in the field. When I started, I took an axe, a 50-meter steel chain, a Silver Ranger, and a duck's back book. But times have changed. So we selected areas throughout the burn to do the plot work. And as we were doing that, we realized that the app didn't really fit our needs. It was more specific to green, mature forests, not sort of that post-burn within the last 10 years. So when we went out and did our plots, the other part is we put in a plot here and there throughout the area. And we brought this information back. And when we brought that back, we realized that between the app, what we were collecting, and the fact that we were only putting in single plots in most areas, that the data was not really, I'll say, robust enough to really give us the answers we wanted. So we went back and had Joanna actually redo the app. And so the old one was on here, and there's obviously subcomponents to each one of these titles. And we added these top 4 categories in the black to help us really nail down the fact that it was post-wildfire. And at the same time, in the green section on the right, we also tweaked some of the subcomponents in there to give us better information. We also realized that we needed to go out and start to sort of bias our plots and put more in and lump them within the same area of similar fuel type, so that the work that Ash does has more data points, I would say, more plots of the same type to help them with the results. So we went out, myself, Kerry McLean, Gareth McDoyle, and a fellow James Henyuth from Telegraph Creek from the Tultans, and we put in a bunch more plots, located those, and from there we ended up with a great sampling of the plots. And along the way, this is just an example of why we're doing this. We saw already, if you look on the right here, what we're calling a non-fuel category is we're not concerned about this from a wildfire perspective. Obviously, at this point in time, there's very little there. Fire would have a real hard time getting in there. But at the same time, we're already coming back to what we call an O1, be a standing grass. And yes, you can see the aspen in there. So lots of grass, which obviously can be a concern, but we weren't able to tell how widespread that is. And this is just another angle of it. And so questions come to our mind: how long till this non-fuel becomes a fuel? Is this going to fall down? Is grass going to come back? What's this going to look like? And at the same time, on the left, although we are starting out with a hazard of grass, the thought is, because of the heavy aspen that is coming back, that will that shade out the grass and actually eliminate that grass, and something else will come back up. So what is right now a hazard, maybe that hazard will be lessened over time as that deciduous grows up and shades out the grass. So needless to say, there's a lot of variability out there. And so the idea is to try to figure out, can we broad brush some areas with the work that Ash doing and be more confident on where the hazard is and how to manage it. And I believe this is where I hand it over to Ash. So go ahead, Ash.
All right, well, thanks so much, Brad. And yeah, grateful for the opportunity. And yeah, thanks everybody for being here. So I'm Ash. I'm a senior data scientist, and I'm representing the BC Wildfire Service and also the Data Science Partnerships Program with Citizen Services. So I just want to mention that this work is really influenced, partly by remote sensing work, and also there's some of that, generalized population health surveillance kind of tabular data influence in there that you might see in the section where we start talking about how to use multiple attributes from the tables at once, or multiple columns. Anyways, so these slides were developed on the traditional territory of the Songhees, Esquimalt, and Saanich people, which is, Victoria. And today I'm grateful to be able to speak from the traditional territory of the Secwepemc people. So I'm in Kamloops today. So we're going to look at the ground data. We're going to look at a mashup with the Sentinel-2 multispectral data. So again, the emphasis is how to get some actionable info with almost no math. So I'll try to keep that accessible for everyone as much as possible. And let's go to the next slide, Brad. So just again, there's the overview of the ground points that Brad and Carrie and their team have collected. So these are awesome. And just a quick note, from that kind of data science perspective, it's like, okay, let's see if we can run some kind of statistical algorithm to take away a few mouse clicks. So I did end up doing a hierarchical clustering, and that was just to group those 100 points into spatial groups that Brad had let me know were there. So they collected they collected 9 groups of sort of related points. So there would be 9, I guess on the next slide, you can see them. I guess the output of that algorithm was just coloring that labeling to put the distinct groups in buckets, just to save me the time of going through the list of 100 things and manually flagging them. So I just wanted to note here that the class 6 and 7 are the O1 fuel type, the grass flammable component that we're primarily interested in, and those are the black triangles there and the little pale blue triangles at the very right. Next slide, please, Brad. Yeah, so just a little brief summary of some of this ground data, and there's quite a few more attributes that we'll be able to get more information out of later. And as you can see, there's fuels information, and the O1 is the class of interest, and there's a bit of deciduous and slash in there, and also a non-fuel class. So just in general, the data are what the stats people would call unbalanced, and there's a lot of interesting attributes, and there's interesting mixing between the groups. So there's all kinds of samples, and none of them are the same. So it's a real ground data set with imperfect real world data that is perfect. Anyway, on the next slide, yes, we had the surface fuel composition and some different types of herbs there. And so depth of organic layer was one other thing that was looked at, and continuity of dead and down material, and so much more. So we don't need to look at bar charts all day, but just before we leave that and get into the sort of the beautiful satellite imagery, here's what you would call co-occurrence plots. They're just counts of how many attributes in different columns appear together, and you can see that there's some of that mixing there. Like on the right, you can see that there's grass in the surface fuel column that will match up with the O1 and the fuel type column, which is also grass. But you can see also that there's a sage bush that's is present in the surface fuel when it's also considered to have enough grass to be flammable and so on. So there's some interesting mixing between different types of labels in the different columns. So it's a interesting real world data set. So I guess on the next slide, we'd be getting into some of the.
Yeah, I just want to mention.
Yeah, go ahead, please.
We are aware that it's not true sagebrush and it's not true pine grass that's out there, but the way the app was built, those were our two categories for selection. So just wanted to throw that out there.
And just having those different perspectives of those different columns gives us information. And yeah, here's an overview on the left of a whole Sentinel-2 tile. That's sort of the format the data comes in. And it's in that familiar red, green, and blue encoding. It's worth noting that there are 9 other colors that are available, so that will selecting those for the color encoding will give you some kind of alien looking image. And just to keep things fun, I put in a Herman comic from 30 years ago. I guess we're all sort of curious if the aliens are going to show themselves. And there's anyway, so here's the Sentinel-2 processing. It's pretty standard. I won't dwell on it too much. So we downloaded data from this year, or just did the standard pre-processing and sort of sampled it all to equal spatial resolution, and sorted everything in time and frequency so that we would have this nice data cube to pull the color fingerprints out of. And on the next slide, there'll be a little video of the different frames, also in an RGB encoding. You see there's a couple October dates, there's a June date, there's a couple July dates. So you see on that window on the right is that's sort of a one-to-one image that's zoomed in. On the left, you see that red square there is represents the part that's zoomed in on the right. So at the bottom you see some scatter plots that are also changing with the date, so you can get an idea of how those color values are represented in space. And that little spectral, the green squiggle there, you'll notice that there's sort of 5 bumps in that. So the Sentinel-2 data is collecting 12 bands. It means it's collecting 12 different colors at every pixel. We've got 5 dates, so that's actually a plot of 60 values, and that's what the image cube looks like at one point of the image. And we'll see later that it's easy to think of that as just like a row in a spreadsheet, and we can do some arithmetic on it to get some results. Lastly, there's a little analysis window at the right there that's showing some of the plot locations quite specifically. So I guess on the next slide, here's a bit of a sample of what some of those little squiggles look like. In this case, you can see we've actually aggregated them by those little clusters that are supposed to represent distinct things. We know there's some variability within those, and you can see it there. So the mean and the standard deviation for those little squiggles, like there's one little spreadsheet row for every sample of that cluster 0 that are in a sort of co-located closely, and they've got some slightly different characteristics. So when you plot the mean and standard deviation, there's a little bit of an envelope around them. And we've plotted that just to give some kind of indication of whether machine learning or just really elementary pattern recognition. In this case, just simple arithmetic. Can we separate those things? And the most obvious thing that stands out is like the class 8 on the top. Actually, you can see that in the winter, which is kind of also the class 1 on the bottom. Is really obvious there. It's obviously different in the winter, and it's kind of it's interesting that this suggests that not only vegetation at the peak growing season can be useful. So I guess you can sort of jump through the next ones pretty quickly, Brad. Yeah, so here's those little squiggles, those little slices of the data cube plotted in such a way that we're calculating their mean and one standard deviation envelope around them. And so there's some different types of, if you go back to that one for just a second. So that one's showing that the sagebush is sticking out pretty clearly in the surface types. And on the next one, if we go back to our fuel type, the O1, which is what we're interested in, it stands out like a sore thumb, also in the summer dates, but even more dramatically in the winter dates, which is pretty interesting. And I think up next, we're gonna, this one is actually a fuel strata gap in meters. So this is actually a spatial parameter. And the kind of unexpected thing is that, multispectral, maybe we're not supposed to be able to measure spatial things. This kind of suggests that we can measure something spatial. And the hypothesis would be that that relates to, observing different vegetation layers as, the leaves are falling off, and so on, or just having different illumination that has different penetration of the vegetation. So on the next slide, there's a bit of a calling it a cumulative sum plot, and that's just arithmetic only. You just add up those curves that we saw before as you go along. And sort of what's fun about this one is that if you see separation between those envelopes on the right, it means that you can just, in your spreadsheet, you can just add up that little spectral squiggle as you go along, and you can potentially make a decision between one thing and another by just drawing a line on the right. And in that case, the class 8 again is really sticking out, and you see that the class 1 is really sticking out on the bottom, and so on and so forth. So there's kind of a matrix of different things that this simple visualization suggests that we can separate. So not everything is obviously going to be separable from everything else, but there's going to be a Venn diagram of what we can separate from what. So like on the next slide, I think, again, in this representation of this cumulative sum representation, we can see that the sagebush really sticks out. There may be some overlap with grass, and so on and so forth. The next slide shows that in this cumulative sum representation, or one is sticking out pretty well. It's showing some overlap with the slash in this visualization, but not in the other one. And it's just nice to try to boil things down to one number if we can, so there's no math and stats. On the next slide, I think this one just brings home that there is some potential for getting 3D information that we might expect to need a LiDAR to get just by combining those multi-temporal observations, which is kind of exciting. Have to explore this further, and there's not a lot of samples because the data set are unbalanced, so we need to look into this further. I think on the next slide, so here's the scary math, and just for humor, I've put a little picture of a scary face, and that's Krampus from Germany, who's kind of like a cross between a Halloween character and Santa Claus. So he's evil Santa Claus anyway. The math here is supposed to be not hard. So this is a demonstration of the idea of a distance concept between colors. So you can see in the first row there's a selection of different color values for a location that we're saying is grass. These are fake numbers, but just so it's obvious to sort of the non-math people. In this example, we're comparing this to a second observation that in this case is also grass. So we're using the same numbers, and in order to get this distance concept for comparing colors, we just subtract those two rows. We multiply the result by itself so that the component we're getting from that color is always positive, so that positive and negatives won't cancel out. At the end, we add everything up to get some number, and lo and behold, we're comparing the colors of grass to the colors of grass. So we get 0. So the more different two things are, the bigger number we're going to get. So things that are more different are going to have a larger value for this simple arithmetic distance concept. So if we go to the next slide, then we can see, we're putting in some color values that aren't the same, and lo and behold, we can subtract and multiply and add everything up, and we get a number that's a lot bigger than 0, and we're good to go. So this distance is kind of that academic math word. It's sort of a meter stick for comparing colors and other things, not spatial distance. So yeah, in this real world example, we have 60 columns because there's 12 colors per date, and we've got 5 dates. So on the next slide, we can see an example of this distance concept in which we've basically repeated that spreadsheet calculation using a grass type, and imagine one row of the spreadsheet for every pixel in the image. So that's quite a lot of calculations, but the computer can do it almost instantly. And just the fundamental sanity check for this result is that there were some clouds in the imagery over here, and there's also some glacier stuff under there, and some clouds on the top, and there's some water bodies and rivers that should not be similar to grass. So in this concept, like a bright value in the grayscale is a large distance. So it's sane that the water bodies and the interference from the clouds and the glaciers and so on, those are far away from grass. So that's good. The other sanity check, if we zoom in into that red box on the right, and if we zoom in even farther, if you look at that little analysis window at the right, that's actually zooming into our grass plots that are sort of at the almost at the top left of that subscene window on the right. We can just do that sanity check to see, okay, it's black over these plots, like our distance concept is showing that we're close to grass, and we're on top of the grass there, so that makes sense. And yeah, on the next slide, we're changing the first row of our spreadsheet calculation. We're changing that to our slash class. So you can see that it still meets the sanity criteria. However, the dark spots that measure things that are close to slash, those have actually moved around, and then that's also good. So if we go to the next slide, we're doing the same thing again for non-fuel, which is it's also meeting that sanity criteria, but the black has moved around as it should, because the non-fuel is not in the same place as the slash and the grass for the most part. So the next step, here's just taking those as an RGB, and the sort of the bluey greeny stuff is going to be the grass. Order O1 is not red, slash is not green, non-fuel is not blue. When we take those distances as this encoding, and on the next slide, we've inverted that so that the red channel representing grass is going to give us red, S1 is green, the non-fuel is blue. So we're going to see the RGB where we expect those things to be, having negated the image that gave a bright value in each of those colors where the things were not. So I think on the next slide, we threshold those colors and find out who wins. So it's the technical word for it is minimum distance classifier. However, as you can see, the things that were most red in the last image are now red, and that's where the grass is. So I think we can jump to the next one. So this is showing. Remember when we set the first row of our spreadsheet to the grass slash and the non-fuel respectively. This is running that distance calculation on the surface fuel attribute instead. There were five outcomes in that column. We're just showing the distances for the three, the dead fines, the grass, and the moss. And what you're seeing here is kind of another sanity check that shows that in that spectral window is highlighted. You can see that if we jump between our different or two clusters of grass sample points, you can see that we're getting the same values of our distance concept there. So everything is sane in terms of the risk that we're trying to locate. On the next slide, I think there's an example of doing that, just simple thresholding, which color wins. That was using that sandwich of distance calculations, one for each of the 5 outcomes in that column. You can see here that the sagebrushes kind of took a bite out of the previous grass result. The absent class, the absent outcome in this column, and the dead finds outcome in this column, they're represented as black because there's 5 distance concepts in that sandwich result, and we're just looking at the first 3. On the next slide, we can see we're just jumping back to that result on the fuel type column again. So to suggest that maybe we could come up with something to look at multiple columns at once, given that this grass type is kind of the risk category of interest for this area. Can we keep things accessible, not use some heavy math stats, and still get some idea about the uncertainty? And on the next slide, we have, you'll notice this is a grayscale result this time. How this is arrived at, remember in the last examples, we calculated a distance measurement, that color concept with respect to the grass outcome and so forth for the fuel type and the surface fuel columns. In this case, we're taking that just the thresholded result that has a 1 in it for the instance in which the grass class has won the competition with the other outcomes in the fields. So we're taking 3 different viewpoints into account. One that uses that black and white 1 or 0 grass is their result from doing that classification, that sort of winner takes all approach on the 3 outcomes in the fuel type. We're doing it again on that surface fuel column, and we're also doing it by running the same algorithm on all those outcomes at once. So we've kind of come up with the Venn diagram thinking that's inspired from that sort of health data kind of work, with MOH and Island Health and others. And what this gives us by adding those 3 models together in terms of 1 or 0 results, basically we're getting some kind of grass index that takes 3 models into account, and it'll give us a result on a scale of 0 to 3, which is kind of non-statistical, but no math required to see where it's coming from. So on the next slide, we're looking at the same. Sorry, Brad, could you go right back to the last one for just a second? So if this one, we're actually zooming into that cluster 7, which has the impure grass targets. So you can see, if we're zooming into our little targets in this analysis window, you can see right there that on this sort of 0 to 3 scale, those ground reference points are actually experiencing a mixed result, which totally makes sense because we know that there's sort of varying degrees of grassiness there from our ground data. And on the next slide, it's just showing, zooming into those. Oh, I forgot to update the arrows here. Sorry. Those should be pointing up at that sort of top left part of the subscene window at the top, where we have our pure targets, and the sanity check is that everything's pure white there. All 3 models are saying that we have grass there. So we're, we have some kind of index that says how confident we are without even doing any stats. So there's, on the next slide.
I was just going to comment.
Oh yeah, please.
At this point, so what that kind of helps for for us on the operational side in the zone, and that is we're starting to see that the majority of the area still is a non-fuel, which from our perspective is caused by what's growing back, but at the same time, there's no horizontal fuel continuity. So even if a fire started in some of those little areas, it can't really go anywhere because there's not a continuous fuel buildup yet. At the same time, what it is showing us is the grass, where the grass, what we're calling slash, that fall down stuff is. So it is identifying the two hazardous fuels out there, or the two fuel types, so that we can see from sort of this broad view that right now it's not a lot of concern because there's a lot of non-fuel. I've spent a lot of time up in this neck of the woods, and just sort of at first glance, when I looked at where it was saying the grass was and where it was saying the fall down was, which is still primarily in the spruce, it all makes sense. Like I say, all the side hills along the Tultan, along the Stikine, the Tuya, and that, they typically are that grass sage component. And at the same time, where the fall down is where is where the spruce was growing now. Next year, we're going to go back in there and ground truth some of this, and at the same time put in some more plots and continue on. So I just wanted to make everyone aware of that.
Thanks so much, Brad. So I guess we've had some encouraging results with detecting potentially even different kinds of shrubs or other non-tree vegetation. And there's kind of this this hope that there might be some 3D info in there as well. So the plan is to collect more data on the ground and from different satellites, work with different partners and scale up, and work on monitoring the forest succession to inform the fuel hazards and operations. And I just wanted to mention that designating some obvious known targets would help reduce some of the false positives, because of the approach that we were using only had those points that we measured. So there's a little bit more work to do to combine all the attributes with confidence and fully leverage all that variability that we have available, so we can use that to help inform the iterations of this analysis sort of longitudinally as they go along. And again, thanks for the opportunity for this, and hoping to collaborate with you if there's a match there. So thanks again for the opportunity, and thanks, Brad, for the awesome project.
Yeah, it's been good. So again, just to target a few folks and agencies, certainly the BDRC for allowing us to present, Joanna Wand, who did up the app for this and made the changes, Tultan Nation, James Henyu, and a few others from the Cassiar Zone, Carrie and Gareth, Dr. Jeff Quinn and the BC Forest Inventory Program, everyone that's supporting us, the Ministry of Citizen Services, and a whole bunch of partners with acronyms that I would only know half of them. But thanks to everybody. And I guess now we can, if there's questions, we'll take them.
Excellent. Thanks so much, Brad and Ash. That was absolutely fascinating.